Hello and welcome to Geo 572, University of Montana and Hydrogeology. So today we're going to talk about some basics of modeling and the art of groundwater modeling in particular. But a lot of this applies to any kind of modeling, and especially physical modeling of earth processes. So we're going to start exploring the art of modeling, how we go about creating groundwater models. And our first topic is a discussion of the generic modeling procedure. So the first thing that guides the creation of a model is the identification of the problem. So throughout the modeling procedure, we're going to construct a model to understand something or answer some question or make some prediction. And that problem is going to guide our modeling. For the entire process. So in general, we're usually often, let's say often, models to make some prediction of interest, right? So the way groundwater may respond to a certain pumping regime, for example. The second thing we do is to conceptualize the system. And this is a super hard and important part of the process, and one that's potentially overlooked in its complexity and its implications on modeling. It's a necessary abstraction of reality or simplification. And it's here that most of our model wrongness gets cooked in. And that's fine as long as we understand what that model wrongness is and how to combat it or even take advantage of it. So once we've conceptualized our system, then we go around model construction. This is more of like the mechanics of taking our conceptual model and building a numerical model. In some respects is quite a bit more simple than the conceptualization process. Here we're just taking the hard part that we did in step 2 and figuring out how to implement it in a given modeling framework. The next step is data assimilation. You might say that this probably occurs along the entire spectrum. So we're assimilating data when we conceptualize it. We're assimilating data when we construct the model. But here, we mean it more specifically, and that is that, let's say we have a prediction of interest, say heads. We might take groundwater heads that we observe and see how our model reproduces those heads, and then modify that model to better reproduce those heads. This sort of data assimilation is where we're taking observations and making sure that our model is at least somewhat representative. reality. All right. Fifth step is what I'm going to call uncertainty analysis. And this is sort of the formal time where we look at how our model compares with data. All right. Once we do all this sort of uncertainty analysis, we might think of the final step for the output as us using the model to then finally address some question. That might be risk assessment, that might be predictive analysis. Or it could be making some kind of scientific inference on a process. Right? And finally, this is where we use our model to get back at that question that we were trying to answer in the first place. Okay, now the second thing that I want to say is this is sort of a general flow, and it looks like it's step by step, but in reality, this is an iterative process. And that is that as we assimilate more data, as we do uncertainty analyses and look at risks, we're probably going to want to go back and understand how our conceptual model affects our outcome, right? And then we rerun through this process again and again and again. And so in a perfect world, this is an iterative process where we refine and better understand our model behavior, how it compares to real behavior, and think of how we can improve. All right. A couple things on modeling. First of all, models are probably best thought of as a way to interpret data and to understand data, and then secondly, as a way to provide guidance on the likelihood or on a potential range of occurrences. The worst thing we could do with a model is expect it to reproduce reality completely, but rather to answer a question about reality. Okay, so we're going to focus in here on this conceptualization and conceptual model. So I want to have a good discussion about how we build models and how we go from the very complicated real world to creating a model that's useful for us to understand or answer a question. Okay, so first and foremost thing that we're going to state is that we create a model and we design a model to answer a question. And the more specific we can be with that question, the better we have a chance of allowing our model to answer that question for us. So our first one of the first things I'm going to do is just draw out some basic principles of modeling. see if I can scale this go down here. And this goes for any kind of model. It's just general fundamental principles that I like to use when I'm modeling. First is your model has a purpose and a specific purpose. The more specific you can be about that purpose, the better. All right? And this purpose is going to guide us from start to finish. The art of modeling is to reduce complexity of the real world. As much as possible, but still allowing us to honestly address the question. Right? We want the simplest model we can to address the purpose. And the reason for this is fundamental in the modeling process. We must produce a model that is a reduction. Right? That is what modeling means. We are coming up with some reduced scale, some reduced smaller portion of the universe that we're trying to understand better. We want to keep our misunderstanding or lack of knowledge of other portions from processes, from allowing us to answer, accomplish a specific purpose. So we need to reduce complexity of the model. All right, this really holds only for physics-based models, but remember that physical model is approximating the solution to the boundary value problem. And we've spent quite a bit of time talking about what we need and techniques we use to go about solving the boundary value problem. All right, and we're trying to solve the boundary value problem most appropriate for our purpose. All right, so we'll go get into this, but essentially, we are trying to construct all the ingredients we need for the boundary value problem and then use one of the methods we've discussed to solve that boundary value And finally, the final principle is uncertainty at the heart and soul. A model that doesn't exactly replicate physical processes should be expected. It's guaranteed. Right? A model that characterizes general system behavior and allows us to ask questions about possibility of different things occurring, or allows us to understand the mechanics of different processes. That is what a model does, and we can't expect it to. And we want to understand that from the very beginning, we've been baking in error and uncertainty for a model. And so we want to recognize this and to utilize it to help us better predict or better understand. Okay. Um, so I think principle A is big enough that we want to take a little more time here. So when we talk about the question which we're trying to answer, we want to be specific as possible. For example, we want to be as specific and quantitative as possible when we start designing our model. So as an example, a model constructed with the purpose of understanding groundwater flow in the Missoula Aquifer is doomed for failure. What does that mean, understanding groundwater flow? It could mean any number of things. How would this model give us this understanding? There's no way to quantify that. Our purpose needs to be specific and quantitative. So something a little closer might be, well, we want to quantify how the change in storage in the Missoula Valley Aquifer, change in storage if we add a new pump that's pumping at a high rate. Okay, that's a little closer. Now we've got something that we might be able to answer. What is the change in storage? But what is our groundwater model actually going to produce? Well, if it's a physical groundwater model, what it really is going to do is, things that we measure, is a change in head across the aquifer. All right, so our model is actually constructed to measure the change in groundwater head across the aquifer. Okay, this is even closer, but again, across the aquifer, that's huge. What does that mean? Our model would be expected to measure the change in head at a set of locations, right? At a set of specific times. So now we have a specific prediction, say delta H, at a set of locations, x1, xn, right? As a function of time, t1 to tn. Right? This very specific prediction is what our model is constructing. Right? The more specific and quantitative we can think about what our goal is, the better we're going to be able to design our model around them. All right, so let's talk about conceptualization and conceptual model. There's a lot of definitions for conceptual model building, and you'll get some of those in your reading, but I'm going to give you mine, and it is this. Conceptual model is where we assemble the ingredients to solve our boundary value. Or our question. All right, and so recall that the ingredients we need to solve a boundary value problem. First one is our coupling equation. Cooked into this governing equation is a lot of things, but a lot of it is what are the physical processes we need to consider. Right? At the conceptual level, we're thinking about what processes are important. What are the physical things that we need to be able to take into account in order to answer the question? We use those to derive applicable. And so it's here where we decide what processes we need to take care of. Second thing was second ingredient, domain interest. Okay, what excuse me, we want to know about the we need to really important and very hard, we need to define appropriate boundaries. So we're going to have to take some section, some piece of the Earth air universe and isolate it. Right? That's a hard thing to do, really cleanly. And finding those boundaries is not easy. So we can think about the size, shape, dimensions. In that, we're going to be implicitly thinking about, well, area / geology. What kind of model do I need? Layering. Okay? So thinking about what our domain of interest is, where our boundaries might be, this is the conceptual model. What dimensions, what shape, three, boundary conditions. Boundary conditions control their solution to the boundary value problem. These are critical for the modeling process. We need to think about what type of boundaries we have. Right? We have three types. Specified value, Here, this might be specified ahead as a function of location and time along some boundary. Right? It's a derivative. Second time, type is unlimited. And this is a specified gradient. So this really is h. This is really specifying grad h on the boundary, and that can be a function of space. All right, and groundwater modeling, this will be specified flux. Because flux is related to versus law. All right, and then the third type is a mixed emission. Cauchy or Robin emissions. And this might be, for example, a flux that depends upon the value ahead. Okay, so we have to define correct boundary conditions that most adequately represent our particular condition. This is really important. All right, fourth thing we need are initial conditions. It's a transient model. What does the model look like? Start. This is a much harder process than might initially meet the eye. We start a model at 4.5 billion years of hydrogeologic evolution that have gotten us to the point where this groundwater system is. We're going to spin up a model that somehow reproduces that. It's not straightforward. The thing we're trying to do is to come up with the best approximation we can. So the example of this would be, well, what's the initial distribution of heads throughout a model domain at time equals 0? So what's the initial distribution of heads for all locations within our domain? All right, fifth, we need to do, start thinking about what the fifth ingredient we need is the parameters that control. So if, for example, consider this P. to this one. The variables in our equation are the things time and rotation variables. Parameters are things like SS, K. These are our, and we need to know their distribution. So this becomes very hard. We don't know what the subsurface is like. We have to figure out how to take the data we have, populate the subsurface. So during conceptualization, the main thing we're trying to do is to construct 1 through 5 conceptually. And while we do that, think about sources of uncertainty and the effective assumptions we've made during our conceptualization. Right? So the end product we want is an abstracted, we call it cartoon. That contains all these ingredients, 1 through 5, right? And that we can use to build a numerical model, make the calculations we need to construct the model. Right, so the end product here is 1 through 5, and an understanding of assumptions, limitations, assumptions. Alternative concepts. Ranges of the parameters. Ranges and distributions. Right? This is this idea that uncertainty in our model is included from the very beginning, including into our conceptualization. Okay, let's stop there. In the next lecture, we'll talk about an example, develop an example model.